All right, welcome to Winter and ECE 353. So can everyone hear me okay-ish? You people at the back might be a bit screwed with the text size, so you might want to move up a little bit. So, welcome back. Hopefully you had a good winter break. And start off, hello, I'm John. I guess my full legal name is Jonathan, but I don't need anything like super fancy. Do not call me my full legal name. Only my parents call me Jonathan when I royally screwed up, so I don't want to hear that name. Just John is fine, nice and easy, real easy, that's it. So I'm a teaching stream professor. I'm fairly new. You may not have seen much about me. I've only taught at UCLA before this, and then here I taught the same course in fall. So I've taught this course once before, so you're not completely screwed, but your only choice is me, and I'm setting your exams now for a change, so good luck. It'll be fine. My exams are usually okay. Don't worry about it. So today's lecture, we'll talk about, just boring course stuff, what to expect, and kind of what is changing with this offering. If you've seen it before and seen that the labs are terrible, hopefully I'll do something to adjust or address that. So Quarkus is the main hub. I don't really like Quarkus, so all it has is a collection of links. So it'll only really post like scheduling announcements on there, like when your midterm is, so it emails you. Other than that, Quarkus is not terribly great, so I'm not going to use it, and your grades will also be posted there, and that's pretty much all you'll use Quarkus for. I'll post all the materials on my website. It'll have links to everything, and if you guys like QR codes, there's QR codes, but if you download the slides from there, everything's clickable. That URL is the materials URL in the Quarkus thing, and everything should be nice and easy. So in a departure, I'm not going to use Piazza. I don't like Piazza. I like Discord. So we'll be using Discord for discussion, lab discussion, Q&As. My philosophy behind that is it's nice, instant. You get instant feedback, and Piazza is okay to like search stuff for, but I want everything there for you. So I'd rather just revise the materials if they are unclear, rather than just having to rely on like, go reference this Piazza post, it answers your question, things like that. And also in a departure, we will, it's also, there's a chat if you prefer to ask questions that way. So it actually pops up, hopefully this works. Oh wow, hey look, it works. So like 25% of you are already on Discord. So just go ahead, message me who you are so I actually know you're enrolled in the course. Then you should see the lectures channel and everything. So that lectures channel will just go there. So if you don't want to raise your hand or do that, you are comfortable with it, whatever, or you just want to add some reactions, like something is really clear, if you just want to like, I don't know, do that a bunch of times, whatever, that is also helpful. And then, so we're going to actually be doing code submission, how real software engineers do code submission, not uploading a zip file or a tar file to some random server. We're actually going to use Git and use an actual open source Git platform. So we'll be using GitLab, that's the URL for it. Again, linked through Quarkus, like 25% of you have already logged in on this, so that is good. It just uses the normal Toronto auth thing, and you shouldn't have to do anything special or email me unlike Discord. And that's how all code submission will be done. Labs are definitely going to change, and I'll talk about that later. But all your code submission will just be you're using Git. If you're unfamiliar with Git, you will learn how to use Git. And that's your code submission is you push your changes, and that's it. So lectures will also be streamed with VOD, so you don't have to worry about panicking and taking down notes if you don't want to. You can go ahead, watch it again if you want, or if anything is unclear. So they'll all be there. It will be exactly like this. Hopefully the audio is going through okay. And while there's still online lectures and live streaming, it does have a delay. It's kind of bad for feedback. So please still attend lectures if you're not sick. If you are sick, this is the thing to keep you away from, getting other people sick, that you have no excuses. Everything's recorded. You can just watch it online. That's kind of my philosophy behind it. But if you aren't sick, you should come. It helps. It's the easiest and most effective way to get feedback, because even without you doing anything, I can look at your faces, and if I say something stupid, I can see your face. It's not that hard to read. While if it's just online, I don't know if I'm doing anything good or anything bad or what. So, and then also here, there's the Discord, or you can feel free, raise your hand at any time if anything is unclear, and I will try and address it. So office hours, I just tentatively set for Wednesdays at 1 p.m. Let me know if there's any conflict. I guess Discord would be the best place for that. Is there any immediate conflict for that? No? Okay, nothing. So the TAs and I will otherwise be in Discord. Most people get their interaction through that way because you don't have to wait for a single hour a week. And I'm generally pretty active on it. And of course, office hours aren't going to be streamed or recorded. That's for you, resource only for you. And of course, as that office hours don't work, you can just email me to meet on something else like Zoom or something like that, or other office hours. So that's completely up to you. So there's going to be at least planned for 6 labs, a midterm, and a final. I don't know if this will actually get approved by the department. They actually haven't approved it yet. I was told that this might not get approved because basically what I did is use their system, made the final exam the lowest percent it could possibly be, then did about half of that for the midterm, and then put all the rest of the grades towards the labs. So it's like 48% labs, 52% written. So I was told by some other professors that it might not slide, but the automated system was all full of green check marks, and they haven't emailed me back yet, so But so hopefully this stays intact, and the final is a bit less stressful with this marking scheme. But this is the planned marking scheme, and you might have heard before that the labs are like really, really awful and really, really time consuming, like 20 plus hours, 40 hours, something like that. So my main job this semester is to make all new labs. So all the labs will be brand new, which means you can't search them on GitHub, which, I won't say the exact percent, but a lot of percent last semester got caught for cheating for doing that. It's generally not a good idea. So you can't do that. 2, we can check it against, your other students. And well, since they're all new labs, there's not going to be that much out there. So that's it. So hopefully, yeah. No, labs are just by yourself. So you can talk to each other about the labs, but you can't, debug other people's labs. The lab, okay, yeah, and the practical sessions will be, the TAs will be there to help you with your labs, but there's no mandatory anything for them. They're just going to be there to help you, and that's it. And there will be no TAs there on Friday. So this Friday won't have any TAs because there's no labs. I'll be releasing the labs, and they'll be due on Mondays. So next Monday will be when the first lab is released, and then you'll have 2 weeks for each lab, and they'll just keep going on and on like that until the semester just kind of ends. So that's the plan for that. And the also intent towards that is, hey, Lab 6 is due the Monday of the last week, so you should actually be done all the course stuff, and then you can actually study for exams, and we can use lecture time for final review or something like that. So I have to mention academic integrity. Toronto takes it really, really, really seriously. They even have like public hearings that you can go see people that got their degrees taken away and all fun stuff like that. It's all public. If you get bored on like a Sunday, I suggest reading it. Some of the cases are actually kind of entertaining, and I didn't know they took it that seriously, but hey, they do. So technically, this also includes not posting any code to GitHub. And I will especially be enforcing this because I don't want to see my assignment stuff posted on GitHub. I know students kind of like to have their GitHub full of stuff that employers can see, but spoiler alert, employers don't care about your course code. They assume that you have done it, and they can read it in your transcript. And because this course is core to everything, you can do something based on the labs that is actually an original piece of software that does something interesting, and it won't be that much different from the labs, and you can actually post it on GitHub, and employers might actually care about it because it's something that's useful. So, yep.
So if we take a portion of the code that we use for the assignments and make our own thing, that's okay, as long as we don't repost your assignments directly.
Yeah.
Okay.
Yeah, so if you take a little snippet, that's fine. Generally, and if you have a little snip in your code, no one's going to go see, you know, your, I don't know, your shell project and steal a little piece of code from it. Like realistically, little code snippets, there's Stack Overflow, there's not going to be anything to do with that. So the code you write is your code, but don't post my full assignments. So you can study together, can't do labs together, they'll be individual. And the idea of this course, and as we'll be doing in the lectures, is making mistakes all the time. And making mistakes, especially for this, is how you learn. If you don't screw up, then you probably haven't actually learned anything, unless, you know, you're like a 1 in a billion person. But I've screwed up lots of things. We're going to screw up lots of things during the lectures, and it's going to be lots of fun. And then don't try and cheat. It makes your life hard. It makes my life hard. It makes the university's life hard. Let's just try and have a nice, fun course. If anything sucks, generally I'm quite fair about it, and I'll make some adjustment if I need to. Yeah.
How does the feedback for the labs work? Like, is it going to be on GitLab, or is it going to be by workers? Like, except for the grade, like what exactly we did wrong on the labs? Like, how are we going to know?
Oh, like feedback for the lab grade? So it should be mostly automated testing, and then there's going to be a TA assigned to each lab that will be able to, that runs a script and might monkey around with it and be able to answer any questions for you.
So we're not going to get like a breakdown of like you did this wrong, you did this wrong.
So there'll be test cases. You'll get the same script probably. I haven't decided or not whether to do hidden test cases, but you'll get a script with some test cases, and it'll say what they failed and why, and then you can fix them. Okay. So there's a few textbooks that are optional. They complement lectures. I try and make everything as self-contained as possible, but this textbook, this Operating Systems in 3 Easy Pieces, is quite good, and it's free, online, PDF, don't have to pay for it. Yep. Yeah, so the question is, how long do the labs usually take? And the answer is, I haven't made them yet, so I don't know. Hopefully, like, you have 2 weeks for them, so 10-ish hours instead of 20, maybe 15, depending on it. But usually with these labs, it's like very inconsistent, your lab time, because sometimes you might just get a bug that just screws you over for like 3 days, and one of your labs might just magically work. So, but ideally like 10, 15 hours, not 20. So yeah, like 10 to 15 is ideal. Probably be a much shorter. Generally, if I can do the lab in under like an hour, under my train ride, then it's probably okay, which is like an hour 40. But I'm probably a lot faster than you. So like 10 to 15. Yeah. Yeah, so when the lab's released, you'll have at least some test cases with it. It's the idea. So hopefully they're going to be, the labs are designed to be kind of shorter to the point, hopefully do something useful and actually reinforce what you've learned in the class. So the labs will all be in C and assume you are running Linux. Some of them you might be able to get away with if you have an M1 Mac. They might kind of work, but since we're using Linux and we are doing operating system stuff, some stuff might not work. Ballpark, like, probably like 3 to 4 of the labs will probably work with an M1 Mac, no problem. The other ones probably won't. First one definitely won't, so you'll have to use a virtual machine or Docker, or if you want to use local development, or use a Linux machine from the university. So they'll all be in C, so if you don't know C, the C programming language book is a good book to know. And we'll have some C examples this class just to make sure that you kind of know what code to expect in this course. So please provide some feedback. I want you to get the most out of this course. This is a really, really foundational and important course. And it will be important to you if you write software, period. So if you write any types of software, this course will make you a better software developer, and I guarantee you about that. So if there's anything you like, dislike, or want to see more of something, just let me know. We have a few lectures of Slack. Yeah.
Are the labs going to be based on the previous labs?
Some, maybe. Others, no. So the question is, are the labs going to be based on the previous labs? And the answer to that is probably not really. Because, yeah, some of them were a bit out there. Like so who here has learned about hash tables before? Hands up if who here has implemented a hash table? Oh, hey, okay, that's pretty good. So, for example, the lab 1 last semester was, one of the parts was implement a hash table as like the warm-up lab, and the incoming students, it was not covered in the data structures course, so they had to learn it completely cold, and some of them took like 40 hours. While you guys would have already done it, and it's kind of an easy thing to do. You probably would have just like copied your code over. But yeah, so all of the labs are going to be, hopefully to the point and useful is my goal. So let's start with an overview of the course. And this is a quote that I like that is ridiculously true, that all problems in computer science and computer engineering can be solved with another layer of indirection. And guess what? An operating system is just another layer of indirection. So all an operating system does is it sits between applications and hardware, and its primary goal is to kind of manage and coordinate resources and otherwise get out of your way. And one of the other really important things is if you want to be good at something in software, you should understand the thing below it. So if you are writing software or writing applications, well, the thing below your applications that interacts with the before it interacts with the hardware, goes through the operating system. So if you know about the operating system, you will be a better programmer. And unfortunately, if you want to be better at operating systems, well, the layer below that is hardware. So you should probably learn more about hardware. But in this course, we'll be learning specifically about operating systems. And generally, we'll be testing your knowledge with more application stuff on top of the operating system instead of going below and going to hardware. Although we'll see, we might have some assembly pop up, here and there. So yeah, how many of you have done assembly? There's some lot. How many of you, did you do ARM assembly? Yes? Okay, so no? What did you do? What? Neos 2? Okay, some of you did some really weird assembly. There's not going to be that much assembly. So if you did ARM, any code examples will actually, I'm transitioning to using something called RISC-V, which is just like an open source ARM that you could actually implement a CPU in if you really wanted to. But I'll do most of my examples using that. But they'll be really minimal. Otherwise, we're pretty much in C land the whole time. So the first question you might want to ask is, well, what is an operating system? And that's actually a fairly complicated question because there's actually no good definition. So Ubuntu and Android, most people would probably consider different operating systems. But if you actually have some knowledge of the internals of an operating system, you know that they both use the same kernel, which is kind of a core part of the operating system that we'll be diving into in this course. So they use the same core part that is like 90% of it, but otherwise you'd consider them, completely different operating systems. So there isn't really a clear line. You might consider those two things the same operating systems if you were just, writing command line utilities or something like that, because both your Android phone, if you were sadistic enough to actually execute command line things, it could do it the same as, a server. But generally, if I'm using an Android phone, I'm not going to just start executing stuff from my command line on my phone. But if you wanted to, you could, and if that was your definition of your application, then they might actually be the same operating system. But most people actually like seeing graphics and are a bit more sane and would probably consider them different operating systems. So if you care about desktop applications, maybe that's your application. So maybe you consider them different operating systems because the way they display graphics is actually different. So for Android, it uses something called Surface Flinger as a library that actually shows you graphics on your screen, while if you're using Linux, it's using something called, at least more modernly, called Wayland. And if you've never dived into the internals, you probably don't know these names, but there are two different display servers to actually show you graphics to your screen. And since they're different, there's different ways of using them, so you might consider them different operating systems if that's what you care about. Okay, so the primary goal of operating systems is to allow you to run more than one application because, if you actually tried to just program on a CPU with no software, well, CPUs are actually quite the dumb things. They just start executing at a fixed address, and whatever code you put there is whatever it executes. So without an operating system, okay, if that's what happens, then I just put my application at that fixed address, and then it starts running, and I'm all good. So that actually works if you are only running one thing on your hardware. So if you're doing any embedded development, which isn't this course, that's perfectly fine. You don't need an operating system. Learn assembly, learn C, carry on with your life. But if you have an operating system, well, the idea behind that is, well, let's use that fixed address, and then it can go to an operating system, and that operating system can start as many programs as it wants. So there's a little bit more to it on a real system instead of just, hey, give me an operating system. It actually points to something that loads the operating system before it boots, but we also won't get into that in this course because booting's kind of boring. So if you do that, you only have one application. Instead, we put an operating system there, and then we let it run multiple applications. So our operating system is going to have abstractions. Everyone has used this abstraction, even though you might not have realized what it was called before. And the first abstraction is a process. And just so you know, abstraction is just a generalization just to make our lives a lot easier. So a process basically abstracts a CPU. So it's just it abstracts a running program. So each process contains its own set of registers, including the program counter, which if we've done assembly, we all know about the program counter. And then when this process starts, one of the things it does is, as part of the information in your program, even though you haven't written it, there's actually an address that tells where the CPU should start executing. Everyone's used C, right? I hope, if you've taken this course. So there's a bit of magic whenever you start running your program. Contrary to what you think, it does not begin at main, and we'll see that during this course. But there's some special things that go on, and we'll kind of break it down and see what actually happens. But your code starting to execute at main is just a nice, happy little lie that we tell you to make your life a bit easier before you take this course and we destroy you. So get ready for that. So I'm just kidding. This course is actually pretty good. It's actually interesting to break it open, see what actually goes on. So if you're the operating system, what you have to do is you have to keep track of registers for all your processes. You have to be able to switch between running processes. And since the operating system controls everything, you actually get to pick what runs. So if you do this poorly, your system might look unresponsive, even though there's actually nothing wrong with it. So it's a really important thing to do. And then you also have to decide when to switch and what to switch to. So those are kind of big engineering trade-offs. There's no perfect answer to that, but we'll see different algorithms you can do to accomplish that and see what actually goes on. So next is talking about memory. So let's assume that we just have a system with like 16 gigs of RAM and we didn't have an operating system. Well, we could, ahead of time, just divide the RAM into like some sections. We can say, hey, operating system, you get the first 4 gigs. Let's say LibreOffice, you get the next 4 gigs. And then Firefox, your web browser, you eat up lots of RAM. So we'll give you 8 gigs. So you could like go ahead and set this as a fixed memory thing. Set this as your memory layout for your physical memory ahead of time. But this is really, really, really inflexible because if LibreOffice, hey, if Firefox isn't even open, well, LibreOffice can't use more than 4 gigs of RAM because Firefox could open, so it needs to leave that space open. And if LibreOffice, went up here and started, writing into this RAM, then, oh no, it might overwrite something with Firefox, and then you just have a whole mess. And then this gets even worse and worse if you want to run multiple applications, right? So if you have your program, you need a space in memory, and then you don't even know how many programs you might run ahead of time. So this just seems like a really, really terrible idea that isn't very flexible. So the concept of virtualization is one of the fundamental things of this course, and it basically fools something into thinking it has all the resources. So we'll get into it kind of midway through the course, but there is virtual memory, so each process thinks it has access to all of the memory on your machine, and it is the operating system's job to maintain that lie. So both LibreOffice and Firefox could actually start executing at the same virtual memory address, so it looks like the same memory address, but in the Firefox process, it's Firefox's code, and in the LibreOffice process, it's LibreOffice's code. But it is the same address. If you were to printf the address of main, assuming it starts there, it would be the same address for both them, but they both contain different things. So we'll get into that kind of midway through the course. But this virtualization concept doesn't end at memory. You can have virtual machines and so on and so forth. So you can just virtualize this all the way to the machine instead of just memory. So this is kind of what I said about virtual memory. Each process believes it has access to everything, and different processes can have the same starting address with different contents. So if you're the operating system, you have to be able to map virtual memory to physical memory, and we'll see this when we get to that. Then you have to keep track of memory usages, like allocations and deallocations, and then you actually have to handle out of memory scenarios. So each process thinks it has access to all of the memory, but your system has a finite amount of memory. So if all the processes use all the memory, then it goes out of memory and you have to do something about it. Spoiler alert, the easiest thing to do is just to kill the thing with the highest RAM usage, and then, hey, it frees your memory. So that's kind of one of the things you can look forward to. So powerful concept. Processes kind of implement virtual CPU with a set of registers. There's virtual memory, and then, like I said before, there's virtual machines as well. So that virtualizes a whole operating system running on a computer, instead of just one-to-one, you can have one physical machine running multiple virtual machines. And then the next topic is going to be concurrency, and this is typically where people have the most amount of trouble with this course, because so far, has anyone ever used threads before? Oh, okay, so some people have used threads before a bit, so you will actually get very familiar with threads, because some of you have this nice thing where, hey, I start executing at main, and it keeps on going, and everything happens in order, and it's all nice. Well, that illusion is now dead, because you'll have multiple things running in the same process at the same time, and you have to manage all of it, and it can lead to very, very hard to debug things. So like even in the Linux kernel, there have been bugs that have survived 7-9 years before anyone actually found them, because they don't happen all the time, and it might take several generations of hardware to even discover the bug. So those are the type of things you have to look forward to. So you also want, the operating system also has to handle this just at a base level, because we have multiple applications running at once, especially if you have a multi-core CPU, which everyone does by now. And you also want applications to do multiple things at once, which you might not have experience with yet, but you will get there. And that is a way to actually utilize all of your hardware and use all of your CPU resources, which again, doing this and maximizing this will make you a much better programmer. So we don't want applications completely isolated from each other either. We want them to be able to communicate in some way, because an application that doesn't communicate at all just kind of heats up your computer, heats up the air, and doesn't do anything useful. Because even your first Hello World application, that does some communication. It prints out Hello World, do something. So you want applications to be able to communicate, and we'll see that. So of course, running one application at a time isn't a great experience. Sorry, there's a question. Are the memories virtual address or physical? So the memory you've been dealing with so far, whenever you run anything and you print the address of something, it has all been virtual addresses so far, and you have not known the wiser. So everything you've dealt with is virtual memory, even though you didn't know it yet. So we will figure out that lie, and actually knowing that will make some concepts, much, much easier. So operating system has to allow multiple executions at once and actually do it safely, and we'll get into some reasons why or how you would actually do that. And you have to manage abstractions for different kinds of inter-process communication. So that's just a fancy word of saying two processes need to talk to each other somehow. So even if you print hello world, something ran your program and then got the information from it. So there is a communication between two programs, even though you only wrote one of them. And that is called IPC, or inter-process communication. And then, of course, if you can communicate, you actually need to make sure that things only communicate with things they should be communicating with. And that will involve permission checking, access control, things like that we'll see. And then finally, we need some persistence. So persistence is just data that's accessible between boots. And the main thing you have for that is a hard drive, which has a file system on it. So a file system just specifies how to organize data on a storage medium, which is typically just flash memory for most people. And the operating system just has to store and retrieve data and also ensure the integrity of it. Because if you wrote your meme to your hard drive, you want to be able to access it later without it being corrupted so you can enjoy it later, right? So the first abstraction that you've all used before, even though you might not have realized it, is a file descriptor. And they abstract both communication and persistence. So what they generalize is just anything that can be written to or read from. So file descriptor, it's just a number. So just some number that you don't know what it represents, and you say, I want to write some bytes there, or I want to read some bytes from whatever that represents. And the abstraction is you don't have to know what it actually represents. It's just a number, and if you write to it, it writes to whatever that represents. So the operating system has to deal with managing to actually writing those bytes to whatever it represents, it might be a file, it might be, another application listing, it might be your web browser, doesn't matter. They're all going to use this kind of interface, and everything's represented by a file descriptor. So it could represent a file or network connection, whatever. So this is to give you a little taste of what to expect in this course. So if you have logged on to the GitLab server, let's see. Oh no. There we go. See, I had something prepared just in case. But I probably should have used it. Okay, so if you log into the GitLab thing, it will look somewhat like this. Although you'll see about half of these, so there'll be some examples. So I'll post all of the code examples there so you can run them, play with them, break them at your will. And then the materials, you probably won't care about that. That's like the actual source code to the slides. But you'll generally probably just want the examples one. So in here already, there is this O1 overview that will have the code we'll get into. So this is an example of kind of the code we'll be looking at. Oh God, can anyone read that like midway? Probably not, eh? Put your hands up if you can actually read that. Okay, so like the first 3 rows, cool. Is that better? All right, yeah, hands up if you can read it. All right, more thumbs up, okay. I guess we're here. Okay, so this is just a simple way to open a file. So if you haven't written C before, if this doesn't make any sense to you, then you should probably review C. But in here, we have main. It has arguments, so we're going to check that it has exactly 2 arguments. If it doesn't, we'll return an error code. So we'll be learning what these error codes are. It's just a special number that the operating system uses. Don't worry about if you don't know what that actually is, but it's just a number. And then we will use a function called open, which returns a file descriptor, which is what I just kind of alluded to. And all it is a number we can read and write from. So it just opens the first argument, which is hopefully a file, and opens it as read only, and we get a file descriptor back. If you actually read the manuals for this, so through the course you will have to read the manual. So of course, if you don't know what the functions do, that's okay. You get to read it later. But open returns a file descriptor if it's successful, and then returns some special value if there's an error that we can check for. So we check for that. Otherwise, there's no error. And then after that, we create an array of 4 bytes, and then call this read function, which takes a file descriptor, and that is reading bytes from something. So if I read bytes from a file descriptor, and I say I want to read 4 bytes, what the operating system will do, so this is a function that we'll see how, but it will kind of call the operating system. So it gets 4 bytes back and fills up that buffer. So if we go through it here, and it returns a number of bytes read. So if we go through all the bytes read, we can read them byte by byte and actually print them out. So what this will do is print out that byte as a normal character if you can actually represent it as a character. Otherwise, it will spit out its hex value, and hopefully you know hex values. If you don't, you will. So that's all this does. So it prints the first 4 bytes of a file. And if we go ahead and run it, so throughout all of this, so there's also these instructions on the slide. So we use Meson as our build system. So the steps will always be like this. So you set up a build directory, and it's already set up. So it doesn't do anything, and then you need to compile your project and tell it where your build directory is, and then goes ahead and builds it. So we made an executable called read4bytes. And read4bytes, whoops, it is in build. So read4bytes just takes a single argument that is a file, so I can be a bit meta about it and read the first 4 bytes of my C file. So the first 4 bytes of my C file, it starts off with an include. So the first few bytes of my include file are, pound INC. So that's the first bit of include. So with this little tool, we get to have some fun with it because you can start poking at a bunch of random things. So everyone's used ls before, I hope, so I can poke it at ls because it's just a file and I can see what it is. You would assume it's just a bunch of garbage machine code, right? Well, the first byte's kind of garbage. It's 7F, doesn't mean much to you, but the rest of it is ELF. Interesting, you can actually read it. And that is not a coincidence. And oddly enough, if I browse other files, I don't know, uname, it also starts with that. And also, if I go really meta, and I see the executable that I'm executing, well, it's also that. Wow. So we'll get into that in the next lecture. So then finally, most kernel code is going to be device drivers, which is like 80+% of real kernel code, like real operating system code. Generally, they're really, really boring. It involves reading a bunch of specifications, realizing they're wrong, and trying to do some hacky workarounds about it. There's generally inconsistencies between them, and it's just a big pain. So if you get into this, you might be stuck doing this, but try and do the fun core work that we'll go into in this course. And don't be stuck doing this because you're just reading a bunch of dry text specs and realizing that they're completely wrong. Because if you go and look at some Linux code, this is an actual comment in the source code making fun of the QA process between some BIOS developers. And a BIOS is just some baseline code your system implements so you can build an operating system on top of it where it does it stands for basic input-output system. So it'll do some basic input-output. So your operating system has to use it. And this is the joke for their QA process where they're just a bunch of people that just write some code, check if it compiles. If it doesn't, they just write some more code. As soon as it compiles, and you can see how old it is, it just checks if it boots Windows 98. And as soon as it boots Windows 98, doesn't matter what the rest of the code works or if it was a fluke or anything, they just ship it and that's the code, and then it is now your problem to deal with. So you can see that, hey, when it was first released, it was bad, and they had to do some really hacky workaround. And then a month later, they actually, did some QA and actually fixed it a bit. So it took about a month to fix it. But the problem with hardware is as soon as you ship it, you can't change it. So you actually have to address it in software and work around it, and it's quite awful. So hopefully you can avoid doing that. So as the teaser to the next lecture, so just to give you a little taste of this course, this is actually Hello World. So hopefully you can read hex. So yeah, oh, that wasn't a question. Okay, so hopefully you can read hex. So here, this is actually Hello World. I don't know why people teach you this in C or like Python or something like this. This is the shortest Hello World you'll ever see that actually executes. So this is 168 bytes, so each of those is a single byte. And believe it or not, this actually works, and I will demonstrate it. So in here, in yours, so it might not actually work for yours. So there is a file called Hello World Linux, arch64, which is ARM. And we can see here that it is 168 bytes. And if I go and execute it, it prints hello world, which is kind of cool. Claps, which is really, really confusing. So everyone's been told so far, like C is low level, it's got no overhead, it's great, right? Okay, well, whoops, not C. Okay, I'll just write this fast. So let's write the easiest hello world we'll see. So include standard.h, int main. Oops. Let's be nice and actually return, whoops. Let's be nice and return 0. So there's my hello source file. Any guesses how big that is by itself? So my source file, it's 74 bytes, pretty good. Now if I go ahead and compile it, let's see how low overhead C is. Any guesses as to how big it is? So hands up if it's, 1,000, under 1,000. Yeah, I've got a few under 2,000. Okay, C's pretty good. Under 5,000. Under 10,000? Under 20,000. Okay, under 1 gigabyte. Okay, that's still not everyone's hands up. Like if people are asleep, geez. Okay, so given that, like probably around like 5 to 10,000. So if I look at it, my hello world is like 14,000. Geez. Low overhead of C. Mine's so much smaller than that. And what's it do? It doesn't do anything special. It just prints hello world. How's that any different than mine? Yeah, it's fine. So, yeah, try that in like JavaScript or something like that, or Python. It gets way worse. So, what I'll leave you at is that there's 3 major concepts in this course. So you'll learn how the following applies to operating systems and also figure out that hello world example: virtualization, concurrency, and persistence. And just remember, I'm pulling for you. We're all in this together.